Alright, let's dive straight into how we describe orientation in 3D space beyond the simple X, Y, Z grid. Think of it like describing how a plane or a robot arm is tilted and turned. We've got these fundamental movements: roll, pitch, and yaw. Imagine you're holding a book. Rolling it side to side, that's roll. Tipping it forward or back, that's pitch. And turning it left or right, keeping the same face up, that's yaw. These three angles, alpha, beta, gamma, can fully define the orientation of any object. Now, how do we translate these physical rotations into math? That's where matrices come in. This UBR matrix is essentially a compact way to represent the combined effect of these roll, pitch, and yaw rotations. It's a 3x3 matrix, and each element Rij tells us about the relationship between the axes of the original frame and the rotated frame. It's the mathematical language of rotation. So, how do we actually get those roll, pitch, and yaw angles from that rotation matrix? It's not magic, it's trigonometry. Look at these formulas. To find the roll angle alpha, we look at the elements R32 and R33. Specifically, it's the arctangent of R32 divided by R33. For the pitch angle beta, it's a bit more involved, involving R31, R11, and R21. The formula uses the square root of the sum of squares of R11 and R21 in the denominator. And finally, for the yaw angle gamma, it's simpler again, just the arctangent of R21 divided by R11. These formulas are the key to decoding the orientation matrix back into the intuitive roll, pitch, yaw angles. They tell us exactly how much the frame has been rotated around each axis. Let's put this theory into practice with a numerical example. Suppose we have a rotation matrix UBR, shown here. This matrix represents the orientation of frame B relative to frame U. Our task is to use the formulas we just saw to figure out the corresponding roll, pitch, and yaw angles. It's like being given a complex instruction manual and needing to figure out the simple steps. We'll plug in the values from the matrix into the equations for alpha, beta, and gamma. Let's see what angles we get. This is a great way to check if our understanding of the formulas is correct. Now, let's talk about Euler angles. This is another popular way to describe orientation, often used in aerospace and robotics. The idea is similar to roll, pitch, and yaw, but the sequence of rotations matters. Think of it like this. First, you rotate around the z-axis, that's your first angle, let's call it alpha. Then, you rotate around the new x-axis, that's your second angle, beta. Finally, you rotate around the new z-axis again, that's your third angle, gamma. Notice how the axes change after each rotation. This sequence of rotations defines the final orientation. The formulas for calculating these angles from the rotation matrix components are slightly different from the roll, pitch, yaw case, but the principle is the same. Decomposing the overall rotation into a series of simpler rotations. Here are the formulas for calculating Euler angles, specifically alpha, beta, and gamma, directly from the elements of the rotation matrix. You might notice they look a bit different from the roll, pitch, yaw formulas. That's because the sequence of rotations and the axes involved are different. For Euler angles, we typically use the z-x-z convention, meaning we rotate around z, then x, then z again. The formulas here show how to extract these angles using the tangent inverse function, just like before. Again, it's a systematic way to decode the orientation matrix into the specific sequence of rotations that produced it. Understanding these formulas is crucial for interpreting and generating orientation data in many applications. Okay, let's shift gears slightly. We've been talking about orientation, but robots also need to move their end effectors, like grippers or tools, to specific positions. This brings us to kinematics, specifically forward kinematics. The diagram shows the basic idea. We know the joint angles and link lengths, the joint link parameters, and we want to calculate the position and orientation of the end effector. Think of it as predicting where the robot's hand will be based on how its joints are bent. The image of the robot arm illustrates this. Knowing the angles θ1 and θ2, and the lengths L1 and L2, allows us to determine the coordinates dx and dy of the endpoint E. We'll focus on serial manipulators, where links are connected in a chain. Methods like Denavit-Hartenberg provide systematic ways to solve these problems. So, what exactly is forward kinematics? It's the process of figuring out the position and orientation of the robot's end effector, the tool at the end of the arm, given the angles and positions of all its joints. If you know how each joint is set, forward kinematics tells you exactly where the robot's hand is in space. The robot model here shows a typical setup, links numbered 0 to n, starting from the base, and joints numbered 1 to n connecting them. The goal is to find the transformation matrix, often denoted as T sub n, which describes the pose of the end effector relative to the base frame. This matrix contains both the position, x, y, z, and the orientation, roll, pitch, yaw, or equivalent, of the end effector. It's the robot's answer to, "Where am I?" To analyze these robot arms systematically, we need a standard way to describe each joint and link. This is where the concept of a generalized link comes in. Think of it as a building block for the robot. Each link has two ends, a proximal end, closer to the base, and a distal end, further out. The link itself has a certain length, represented by a sub-I, and a twist angle, alpha sub-I, which describes how the axes of adjacent joints are oriented relative to each other. This diagram visually represents these parameters. The link length, a sub-I, is the distance between the joint axes. The twist angle alpha sub-I is the angle between the projection of the axis of joint I onto the plane perpendicular to the axis of joint I minus 1. These parameters are fundamental for defining the robot's geometry. Now, let's look at how these links and joints are connected. This diagram shows two consecutive links, link I-1 and link I, connected by a joint. We need to define the relationship between the coordinate frames attached to these links. Typically, we attach a frame to the distal end of each link. The key parameters here are the joint angle theta I, which describes the rotation of the joint, and the joint distance di, which is the offset between the joint axes along the previous z-axis. Also important is the link length ai and the link twist alpha I, which we discussed earlier. These four parameters together, ai, alpha I, di, and theta I, are the core of the Denavit-Hartenberg convention. They completely define the relative position and orientation of one link frame with respect to the previous one. Let's clarify the joint types. In the DH convention, we primarily deal with two types of joints: revolute joints, which are like hinges or elbows, allowing rotation, and prismatic joints, which are like sliders or telescopes, allowing linear movement. For a revolute joint, the variable we care about is the angle of rotation, theta I. For a prismatic joint, it's the linear displacement, di. We can combine these into a single generalized joint variable, qi. So, qi equals theta I for a revolute joint, and qi equals di for a prismatic joint. This simplifies notation when dealing with robots that have a mix of joint types. The diagram shows an example where alpha I minus 1 equals 0 and alpha I plus 1 equals 0, indicating specific orientations of the joint axes. The definition of qi is crucial for setting up the equations of motion. Okay, now for the star of the show, the Denavit-Hartenberg convention, or DH convention. This is a powerful, systematic method for assigning coordinate frames to each link of a robot and identifying the four key parameters that define the relationship between adjacent frames. It's like a recipe for building the mathematical model of the robot. The four DH parameters are ai, the link length, the distance between the joint axes, alpha I, the link twist, the angle between the joint axes, di, the joint distance, the offset between the joint axes along the previous z-axis, and theta I, the joint angle, the rotation of the joint. By defining these four parameters for each joint, we can build a complete description of the robot's structure. This convention is fundamental for deriving the forward kinematics equations. Once we've assigned frames and identified the DH parameters for all the joints, the next step is to calculate the homogeneous transformation matrices. Each matrix, say T sub I to the power of I minus 1, represents the transformation from the frame attached to link I minus 1 to the frame attached to link I. This matrix is built using the 4 DH parameters for that joint. After calculating these individual transformation matrices, we multiply them together in sequence. Starting from the base frame, 0, we apply the transformation to get to frame 1, then apply the transformation from 1 to 2 to get to frame 2, and so on, until we reach the end effector frame, n. This final product, the composite transformation matrix, often written as T sub n to the power of 0, gives us the complete pose, position, and orientation of the end effector relative to the base frame. This is the heart of the forward kinematics solution. Let's quickly revisit the DH parameters and their behavior for different joint types. For a revolute joint, the joint angle theta I is the variable. The parameters AI, alpha I, and di are typically constants or fixed values. For a prismatic joint, the joint distance di is the variable. The parameters AI, alpha I, and theta I are usually constants. The DH algorithm involves a specific sequence of steps, defining the z-axis of the current frame, finding the x-axis, locating the origin, and then determining the parameters AI, alpha I, di, and theta I. The diagram shows the typical flow of this algorithm. The HTM mapping diagram visually represents the screw displacement concept. The joint motion combines a rotation around the z-axis and a translation along the x-axis. This systematic approach ensures consistency across different robot designs. How does the DH convention actually work mathematically? It breaks down the transformation from one frame to the next into a sequence of simpler operations. Typically, it involves a rotation around the previous z-axis, a translation along the previous z-axis, a rotation around the new x-axis, and a translation along the new x-axis. The formulas shown here represent these operations using homogeneous transformation matrices. Trans of z hat, d, I means translating a distance d, I along the z-axis. Rot of z hat, theta, I means rotating by angle theta, I, around the z-axis. Similarly, trans of x hat, ai, and rot of x hat, alpha, I, are translations and rotations around the x-axis. The final transformation matrix, I to the power of minus 1t, I, is the product of these 4 basic transformations. This decomposition makes it easier to derive the overall transformation matrix for each joint. Let's visualize this with a simple 2DOF manipulator. It has 2 links, link 1 and link 2, connected by 2 joints, Joan and J2. The base is link 0 and the end effector is attached to link 2. The kinematic diagram shows the structure. According to the DH convention, we assign a frame to each link. The transformation from the base frame to the end effector frame is found by multiplying the individual transformation matrices for each joint. So, we calculate the transformation from frame 0 to frame 1, then from frame 1 to frame 2. The composite transformation matrix, 0T2, is simply the product of these 2 matrices. This matrix 0T2 will give us the position and orientation of the end effector P relative to the base frame. This is the essence of forward kinematics for this simple case. This diagram summarizes the process. We start with the base frame, 0, and the end effector frame, n. The transformation between each pair of adjacent frames, I-1 to I, is given by the matrix I-1 Ti. This matrix is derived from the DH parameters for the joint connecting frames I-1 and I. To find the overall transformation from the base to the end effector, we perform a chain multiplication of these individual transformations. The equation 0Tn equals 0T1 times 1T2 times 2T3 times dots times n-1Tn is called the loop closure equation. It's essentially saying, the transformation from the base to the end effector is the same as going through each joint step by step. This equation is the foundation for solving forward kinematics problems. The composite transformation matrix, 0Tn, is incredibly important. It fully describes the pose of the end effector frame relative to the base frame. It's a 4x4 matrix, but the bottom row is always 0, 0, 0, 1. The top left 3x3 portion of the matrix is the rotation matrix, which tells us the orientation of the end effector. The top right 3x1 column vector is the translation vector, which tells us the position of the end effector. The diagram shows the general structure of this matrix. The elements ux, vx, wx, etc. represent the direction cosines of the end effector axes relative to the base frame. Dx, dy, dz are the coordinates of the end effector's origin relative to the base frame. This matrix is the output of the forward kinematics calculation. Let's apply this to a concrete example, a 2DOF manipulator. The diagrams show the robot arm with two links, lone and lu, connected by two joints, jon and j2. The angles θ and θ are the joint angles we control. Our goal is to find the position of the endpoint P, given these angles and the link lengths. This is a classic problem in robotics, often solved using trigonometry. We can use the law of cosines or break down the vectors into components. The first diagram shows the general setup, the second diagram highlights the joint nodes and link lengths. We need to express the coordinates of point P, let's call them x and y, in terms of θ1, θ2, lone, and los2. To solve this systematically, we use the Denavit-Hartenberg convention. First, we assign coordinate frames. Frame 0 is fixed at the base. Frame 1 is attached to the end of link 1, and frame 2 is attached to the end of link 2. The diagram shows the frames and their axes. Next, we create the DH parameter table. For this 2DOF robot, we have two joints. The table lists the DH parameters for each joint, θi, di, ai, and alpha I. For joint 1, θ1 is the joint angle, d1 equals 0, a1 equals L1, and alpha 1 equals 0. For joint 2, θ2 is the joint angle, d2 equals 0, a2 equals L2, and alpha 2 equals 0. These parameters are derived from the geometry of the robot. With the DH table, we can now calculate the transformation matrices. Using the DH parameters, we can write the transformation matrices. For the first joint, the transformation from frame 0 to frame 1 is given by the product of rotation and translation matrices. Since alpha 1 equals 0 and d1 equals 0, some terms simplify. The formula for 0t1 is shown. Similarly, for the second joint, the transformation from frame 1 to frame 2 is 1t2. Again, since alpha 2 equals 0 and d2 equals 0, the formula simplifies. The composite transformation matrix 0t2 is then found by multiplying 0t1 and 1t2. The resulting matrix, shown in the expanded form, contains the cosine and sine terms of the joint angles θ1 and θ2, and the link lengths L1 and L2. This matrix is the forward kinematics solution for this specific 2DOF robot. Let's look at the structure of the resulting transformation matrix, 0t2. The top left 3x3 part is the rotation matrix. The elements involve cosines and sines of the joint angles θ1 and θ2. The top right 3x1 column vector contains the position coordinates of the end effector. These coordinates depend on the link lengths L1 and L2 and the joint angles θ1 and θ2. The bottom row is always 0, 0, 0, 1. The diagram on the left shows the matrix structure, highlighting the rotation and translation parts. The diagram on the right shows the matrix when both joint angles are 0, which corresponds to the home position. In this case, the end effector is at the origin, and its orientation matches the base frame. This confirms our calculations are correct. This diagram puts it all together. The upper part shows the forward kinematics equation we derived. The position vector x, y, of the end effector P is related to the joint angles θ1 and θ2 and the link lengths L1 and L2. The lower part is the kinematic diagram of the 2DOF arm. It shows the two joints, the two links, and the coordinate frames. The axes x0, y0, z0, x1, y1, z1, x2, y2, z2 help visualize the transformations. The displacement vector dx, dy represents the position of the end effector P. By applying the forward kinematics equations, we can calculate dx and dy for any given theta 1 and theta 2. This is the fundamental capability of forward kinematics. Now, let's consider a slightly different robot, one with a mix of joint types. This example has a revolute joint, Joan, controlled by angle theta 1, and a prismatic joint, J2, controlled by linear displacement d2. The diagram shows the structure and the coordinate frames. The DH parameter table needs to be adjusted for this case. For joint 1, theta 1 is variable, done equals 0, on equals lone, and alpha 1 equals 90 degrees, because the z-axis of frame 1 is perpendicular to the z-axis of frame 0. For joint 2, theta tau equals 0, d2 is variable, a tau equals 0, and alpha tau equals 0. The difference in alpha values reflects the change in the orientation of the joint axes. We'll use these parameters to derive the transformation matrices. Continuing with the mixed joint type example. The DH parameter table confirms the setup. Theta 1 is variable, d1 equals 0, a1 equals l1, alpha 1 equals 90 degrees. For joint 2, theta 2 equals 0, d2 is variable, a2 equals 0, alpha 2 equals 0. The transformation matrix 0t1 now includes a rotation around the x-axis due to alpha 1 equals 90 degrees. The formula for 0t1 is shown, involving rod of z, theta 1, and rod of x, 90 degrees. The transformation matrix 1t2 is simply a translation along the z-axis, given by trans of z, d2. The composite transformation 0t2 is the product of 0t1 and 1t2. The resulting matrix structure is shown, showing how the joint angle theta 1 and the joint displacement d2 affect the end effector's position and orientation. Let's look at another example, a 3-DOF manipulator with 2 prismatic joints. This robot has a revolute joint, Joan, controlled by angle theta, and 2 prismatic joints, J2 and J3, controlled by displacements d2 and d3. The diagram shows the structure. The DH parameter table needs to reflect this configuration. For joint 1, theta 1 is variable, done equals 0, on equals lone, alpha 1 equals 0. For joint 2, theta 1 equals 0, d2 is variable, a2 equals 0, alpha 2 equals 0. For joint 3, theta 3 equals 0, d3 is variable, a3 equals 0, alpha 3 equals 0. The key difference is that now we have 2 prismatic joints, meaning 2 of the joint variables are linear displacements. We'll proceed with the same steps. Define frames, create the DH table, and calculate the transformation matrices. The composite transformation matrix for this 3-DOF manipulator, 0tn, will have a similar structure to the previous examples. The top left 3x3 part is the rotation matrix, and the top right 3x1 column is the translation vector. The diagram shows the general form. The elements lambda ij are functions of the joint angles and link lengths, while dx, dy, dz are the position coordinates of the end effector. The bottom row is always 0, 0, 0, 1. The key takeaway is that the forward kinematics solution provides the complete pose of the end effector in terms of the joint variables. This is essential for controlling the robot to reach desired positions and orientations. We've spent a lot of time on forward kinematics, figuring out where the robot is given the joint angles. But what if we know where we want the robot to be, and we need to figure out the joint angles required to get there? That's the inverse kinematics problem. It's like asking, if I want my robot's hand to be at this specific point in space, what should I bend the joints to? The diagram shows the relationship. Forward kinematics goes from joint variables to end effector pose. Inverse kinematics does the opposite. Solving inverse kinematics is generally much harder than forward kinematics. It's often non-linear, and there might be multiple solutions, or even no solution at all, depending on the robot's configuration and the desired pose. So, what is inverse kinematics, really? It's the process of finding the joint variables, the angles and displacements of the robot's joints, that will result in the end effector achieving a specified position and orientation. Given the desired pose of the end effector, represented by the transformation matrix C, we need to solve for the joint variables Qi. This is the reverse of forward kinematics. The handwritten note summarizes this. Given the desired position and orientation of the end effector, find the joint variables. The challenge lies in solving the equations that relate the joint variables to the end effector pose. This is a central problem in robot control and path planning. Let's revisit the 2DOF manipulator example, but this time from the perspective of inverse kinematics. The diagram shows the robot arm and the desired end effector position P. We know the desired position and orientation, represented by the matrix 0Tn. Our goal is to find the joint angles θ1 and θ2 that achieve this. The note mentions that there might be multiple solutions, like θ1, θ2, and θ1 prime, θ2 prime, which could correspond to different arm configurations reaching the same point. The joint variables are systematically represented by Qi, which is θi for revolute joints and di for prismatic joints. The end effector's location is defined by both its position and orientation. Solving for these joint variables is the core of the inverse kinematics problem. Why is solving inverse kinematics so difficult? Several reasons. First, the equations are often highly nonlinear. Think about the trigonometric functions involved in the forward kinematics. Second, they are simultaneous equations, meaning the joint variables are all intertwined. Third, they are transcendental equations, which means they can't always be solved algebraically. Furthermore, the number of equations might be greater than the number of unknowns, leading to coupled or dependent equations. As a result, the inverse kinematics problem can have several outcomes: a unique solution, multiple solutions, or sometimes no solution at all. For a robot to have a solution for all possible positions and orientations within its workspace, it must have enough degrees of freedom, DOF. The number of DOF must be at least equal to the number of independent constraints imposed by the task. Having sufficient DOF is necessary, but not always sufficient for a solution. Let's try to find a closed-form solution for the inverse kinematics of our 2DOF manipulator. Closed form means we want an algebraic expression for the joint angles θ1 and θ2 in terms of the desired end effector position dx and dy. The diagram shows the robot and the desired position. The bottom table shows the forward kinematics matrix 0T2. The position part of this matrix is given by the vector L1 times C1 plus L2 times C12, L1 times S1 plus L2 times S12, 0, where C1 is cosine of θ1, S1 is sine of θ1, C12 is cosine of θ1 plus θ2, and S12 is sine of θ1 plus θ2. Our goal is to solve these equations for θ1 and θ2. This is a classic problem with a well-known geometric solution. We start with the forward kinematics equations for the position part. The x-coordinate is dx equals L1 times C1 plus L2 times C12. The y-coordinate is dy equals L1 times S1 plus L2 times S12. Here, C1 equals cosine of θ1, S1 equals sine of θ1, C12 equals cosine of θ1 plus θ2, and S12 equals sine of θ1 plus θ2. We need to solve for θ1 and θ2. The matrix C represents the desired configuration matrix, which contains the known values dx, dy, and the unknown joint angles θ1 and θ2. The handwritten note clarifies that the matrix C is a function of the desired position and orientation of the end effector. Our task is to invert this relationship to find θ1 and θ2. To solve for θ1 and θ2, we can use a geometric approach. First, consider the triangle formed by the two links and the line connecting the base to the end effector. The length of this line is the distance from the origin to the point dx, dy, let's call it r. Using the law of cosines on this triangle, we can relate r, L1, and L2. The equations for dx and dy are shown. The first step is to eliminate the angle θ1 plus θ2. We can do this by squaring and adding the equations for dx and dy. This gives us dx squared plus dy squared equals L1 squared plus L2 squared plus 2 times L1 times L2 times cosine of θ2. This equation relates the desired position dx, dy to the joint angle θ2. Let's work through that algebra. We start with dx equals L1 times C1 plus L2 times C12 and dy equals L1 times S1 plus L2 times S12. Squaring both equations and adding them, we use the identity c squared plus s squared equals 1. After simplifying using trigonometric identities, we arrive at the equation dx squared plus dy squared equals L1 squared plus L2 squared plus 2 times L1 times L2 times cosine of theta 2. Rearranging this, we can solve for cosine of theta 2. Cosine of theta 2 equals dx squared plus dy squared minus L1 squared minus L2 squared divided by 2 times L1 times L2. This gives us the value of cosine of theta 2. Knowing cosine of theta 2, we can find sine of theta 2 using the identity sine squared of theta 2 plus cosine squared of theta 2 equals 1. This gives us sine of theta 2 equals plus or minus the square root of 1 minus cosine squared of theta 2. The plus or minus sign indicates there might be two possible solutions for theta 2. Now that we have sine of theta 2 and cosine of theta 2, we can substitute back into the original equations for dx and dy to solve for theta 1. Let's take the equation for dx. We can rewrite it using the cosine addition formula. Cosine of theta 1 plus theta 2 equals cosine of theta 1 times cosine of theta 2 minus sine of theta 1 times sine of theta 2. Substituting this into the equation for dx, we get dx equals L1 times cosine of theta 1 plus L2 times cosine of theta 1 times cosine of theta 2 minus sine of theta 1 times sine of theta 2. Rearranging terms, we can factor out cosine of theta 1 and sine of theta 1. This gives us dx equals cosine of theta 1 times L1 plus L2 times cosine of theta 2 minus sine of theta 1 times L2 times sine of theta 2. Let's define KL equals L1 plus L2 times cosine of theta 2. Then we have dx equals cosine of theta 1 times KL minus sine of theta 1 times L2 times sine of theta 2. Similarly, we can work with the equation for dy. Using the sine addition formula, sine of theta 1 plus theta 2 equals sine of theta 1 times cosine of theta 2 plus cosine of theta 1 times sine of theta 2, we substitute into the equation for dy. This gives us dy equals L1 times sine of theta 1 plus L2 times sine of theta 1 times cosine of theta 2 plus cosine of theta 1 times sine of theta 2. Rearranging terms, we get dy equals sine of theta 1 times L1 plus L2 times cosine of theta 2 plus cosine of theta 1 times L2 times sine of theta 2. Let's define Ks equals L1 plus L2 times cosine of theta 2. Then we have dy equals sine of theta 1 times Ks plus cosine of theta 1 times L2 times sine of theta 2. Now we have two equations, dx equals cosine of theta 1 times Kl minus sine of theta 1 times L2 times sine of theta 2, and dy equals sine of theta 1 times Ks plus cosine of theta 1 times L2 times sine of theta 2. We can solve these simultaneously for cosine of theta 1 and sine of theta 1. Dividing these equations gives us tangent of theta 1 equals dy divided by dx. From here, we can find theta 1 using the attantual function, which handles the quadrant correctly. The formula for theta 1 is shown, using the k values defined earlier. Let's apply this to a numerical problem. Suppose we have a 2-DOF manipulator with link lengths L1 equals 5 and L2 equals 7. We want the end effector to be at position dx equals 9.1416 and dy equals 14.7984. The matrix C represents the desired configuration. The first two rows contain the rotation matrix elements, and the third row contains the translation vector dx, dy, dz. The fourth row is 0, 0, 0, 1. The diagram shows the robot arm and the desired position. We need to calculate the joint angles theta 1 and theta 2 that achieve this position. We'll use the formulas we derived for the closed form solution. Let's move to a more complex example, a 3-DOF articulated arm, also known as a TRR manipulator. This robot has 3 revolute joints, Joan, J2, and J3, connected by 3 links, Lone, L2, and L3. The diagram shows the structure. The goal is to find the joint angles theta1, theta2, and theta3 that will position the end effector at a desired point. This is a common type of robot used in industrial applications. The problem becomes more challenging because we now have 3 joint angles to solve for. The forward kinematics equations will be more complex, and the inverse kinematics solution might involve more steps or geometric considerations. To analyze the 3-DOF arm, we need to define coordinate frames. The diagram shows the frames attached to the base, link 1 and link 2. Frame 0 is fixed at the base. Frame 1 is attached to the end of link 1, and frame 2 is attached to the end of link 2. The joint axes are defined as follows. The z-axis of frame 0 is vertical, the z-axis of frame 1 is perpendicular to the plane of the paper, and the z-axis of frame 2 is also perpendicular to the plane of the paper. The x-axis of each frame is chosen to be perpendicular to its respective z-axis. The joint angles θ1, θ1, and θ3 are measured around the z-axis of frames 0, 1, and 2, respectively. The link lengths ln, 2, and 2, 3 are the distances between the joint axes. With these frames defined, we can proceed to derive the forward kinematics. The forward kinematics model for the 3-DOF arm involves calculating the transformation matrix from the base frame to the end effector frame. This matrix depends on the joint angles θ1, θ2, and θ3. The diagram shows the structure of the transformation matrix. The top left 3x3 part is the rotation matrix, and the top right 3x1 column is the translation vector. The elements of the matrix involve cosine and sine terms of the joint angles and the link lengths L2 and L3. The bottom row is 0, 0, 0, 1. Now, let's assume we know the desired position and orientation of the end effector, represented by the configuration matrix C. The matrix C is known. We need to equate the forward kinematics model to the configuration matrix C and solve for the joint angles θ1, θ2, and θ3. This leads to a system of equations that we need to solve. Let's consider a 4-DOF articulated manipulator. This robot has 4 joints, J1, J2, J3, and J4, connected by 4 links, link 1, link 2, link 3, and link 4. The diagram shows the structure and the coordinate frames. The joint variables are Q1, Q2, Q3, and Q4. The forward kinematics model will involve calculating the transformation matrix from the base frame to the end effector frame. This matrix will depend on the joint variables Q1, Q2, Q3, and Q4. The complexity of the forward kinematics model increases with the number of joints. For a 4-DOF manipulator, the transformation matrix will be more complex than for the 3-DOF arm. The inverse kinematics problem will also be more challenging. The diagram shows the structure of a 4-axis SCARA manipulator. SCARA stands for Selective Compliance Assembly Robot Arm for Automation. This type of robot is commonly used in pick-and-place operations. It has 4 joints, J1, J2, J3, and J4. The first 2 joints are typically revolute joints that allow the robot to move in the horizontal plane. The third joint is a prismatic joint that allows vertical movement. The fourth joint is often a revolute joint that allows the end effector to rotate. The diagram shows the coordinate frames attached to each link. The joint variables are θ1, θ2, Q3, and θ4. The link lengths are M, S, D3, and G2. The forward kinematics model will involve calculating the transformation matrix from the base frame to the end effector frame. This matrix will depend on the joint variables θ1, θ2, Q3, and θ4. Now, let's shift our focus to velocity kinematics. Instead of just positions, we're interested in how fast the robot is moving. How does the speed of the joints relate to the speed of the end effector? The question, how fast can this move, highlights the importance of velocity analysis. The diagram shows the relationship between joint space and Cartesian space. Forward kinematics maps joint angles θ to Cartesian position x. Inverse kinematics maps Cartesian position x back to joint angles θ. Velocity kinematics relates the joint velocities θ dot to the end effector velocity x dot. This relationship is captured by the Jacobian matrix, J. The equation x dot equals j times theta dot describes how the end effector